Okay, yesterday we tried to stress um, a way of solving partial gas law problems. And the reason that I did this is because a lot of you guys learn by algorithm, but don't have a good way of checking yourself as you're doing work. So, as we look at something that looks like our ideal gas law, our PV over NT equals R. One way of looking at this is that it tells you the relationships between P and V, between P and N, between P and T, and so forth. So we can look at this and say that P is inversely related to V, right? We can tell that because they're next to each other, because so we know that P times V has to be a constant, right? The power of something like this is that we know that as P goes up, V goes down. And so that means that if you have a problem like something like a sample of gas um, at 105 kPa has a volume of 120 milliliters, right? What volume will it have at, I don't know, 600 kPa? Okay. And so now we have two pressures and a volume. And you want to know what's going to happen. Well, we know that the pressure is going up. That means the volume must go down, right? Must go down. Just saying. And right, so the volume must go down, and that means that when we do this, we could do this as a factor label problem, and we could say we have 120 milliliters times some fraction equals the new volume. And if we want to do that, we know that this fraction has to be uh, less than 1. Right? It has to be less than 1 because when you multiply by it, it makes a smaller volume. Right? And so we have 600 and we have 105. If I put 600 in the top and 105 in the bottom, I get a number bigger than 1. So instead, I'll put 105 kPa in the top, 600 kPa in the bottom, and now I've solved my problem. 120 times 105 over 600 is my new answer, and that would be, I guess, whatever it is, 21, right? 21 milliliters. Okay. Um, don't you see? So we can solve a lot of these by knowing the direction of the change, even if we don't memorize the specific equations. Now we could also solve this using P1V1 equals P2V2, which we can get right from this same equation. I'm not saying you can't solve it by algorithm, but if you can remember what this implies, that as P goes up, V goes down, you can tell whether you've multiplied properly or improperly because your answer will either be larger or smaller depending on that relationship. And so it becomes a simple factor label problem if you can remember the concept. So just to kind of go over it one more time, let's suppose we have a problem something like, I don't know, 50 liters of gas at, I don't know, 300 degrees Celsius is cooled to, 50 degrees Celsius, right? What is the new volume of the gas? Okay, so we can have something like this. Well, if we think of what the relationship is, PV over T equals R. Well, that implies that V over T is a constant, right? So that means that as V goes up, T goes up, right? This is a direct relation. Right? And you probably know this from past experience anyway, that as temperature is increased, gases tend to puff up. So you already know what direction things go. So in this case, the temperature is going down. So the volume must go down. Right? Now, that means that you can take our 50 liters times a fraction. And again, it has to be less than 1 because volume must be going down, right? So we need to take our two temperatures and put them in here. The one problem here is that we need to always remember that we need absolute temperatures, right? So 300 degrees Celsius is the same thing as 573 Kelvin. 50 degrees Celsius is the same thing as 323 Kelvin. And so our number that's less than 1 is going to be 323 Kelvin over 573 Kelvin, right? And that's going to equal our new smaller volume, right? And so when we do that, I don't know what we get off the top of my head, something like 1/11 of this. Yeah, this is a job for a calculator. And so we say 50 times 323 divided by 573 equals, and we get 28.2, or actually 28 since we only have 2 digits in the 50. So 28 liters, okay, is our new smaller volume. Okay. Anyway, you can also, again, plug it into V1 over T1 equals V2 over T2. But if you can remember what the direction is, you know what you're going to have to scale your answer to without actually formally plugging it into an equation, right? You know that you're going to have to multiply a volume by some ratio, either less than or greater than 1, depending on your understanding of the pattern, okay? And so this is a really powerful way of thinking about gas laws. That's one of the reasons that we stress the particle in the box model, and one of the reasons we stress understanding this relationship in terms of direct and inverse, because it helps you know whether your answer has gone in the right direction and whether you followed the proper proportion.